This is the final section in Chapter 3, and it is titled Distribution Classes. Various distribution classes have been defined to distinguish sets of distributions from one another by certain properties of the failure time distributions. We're going to look in detail about 4 of these distribution classes. They are IFR, which stands for increasing failure rate, DFR, which is decreasing failure rate, IFRA, which is increasing failure rate on the average, and DFRA, which is decreasing failure rate on the average. There's an important theoretical result that's known as the IFRA closure theorem, which we will run into along the way. And it says when all of the components of a coherent system have IFRA distributions, then the system lifetime is in the IFRA class. And as before, we will assume independent failure times in order to achieve the IFRA closure theorem. So here is a definition, and in fact this is 2 definitions in one. We're going to define both IFR and DFR classes in one definition. A lifetime distribution is IFR if h of t is non-decreasing in t. Now you'll notice that the letter I, which stands for increasing, in this case, is used very loosely. The increasing that reliability people use really means non-decreasing to a mathematician. And this is an important distinction. When you say that IFR is non-decreasing in t, what that allows you to do is have some distribution with a constant hazard function, and you know what that distribution is. That's the exponential distribution, to serve as a boundary between the 2 classes. So if you look at our Venn diagram down here, there is only one distribution that sits at the intersection of the IFR and DFR classes, and that is the exponential distribution. On the other hand, if you want a hazard function which is strictly increasing, then an example which we've seen before of a distribution with an increasing, strictly increasing survivor function is a Weibull distribution with kappa greater than 1. Over here, if you want an example of a distribution which is in the DFR class, and the DFR class says that h of t is non-increasing in t. So an example of that is, again, the Weibull distribution, but this time the Weibull distribution with a kappa value that falls between 0 and 1. And kappa is the shape parameter. Finally, for the Venn diagram here, is there anything that falls outside of IFR and DFR classes? And we've seen 2 of those already. One such example is the BT class, bathtub-shaped hazard function. Another one is the upside-down bathtub-shaped hazard function. And there are many, many others. Those are just a couple examples. So by defining IFR and DFR distributions in this fashion, we get 4 different sets of distributions, and all distributions will fall into one of those 4 sets on the Venn diagram. Here are a couple operations that we can do on lifetimes. Let's say we've got n lifetimes, and we're going to assume that those are mutually independent lifetimes. What are some operations we can do on lifetimes? Well, the first thing we can do is we can add them up, take a sum. And that applies to a passive standby system. Second thing we can do is we can take a mixture of these random variables. That is, if T1 has survivor function S1 of t, T2 has survivor function S2 of t, up to Tn having survivor function Sn of t, if we can come up with some constants P1 through Pn, which are positive and sum to 1, then what we get in that case is we get a survivor function of a mixture of those distributions, and we'll see more about mixtures out in Chapter 5. What are some other operations we can do on lifetimes? Well, we could form a coherent system. We could take those n lifetimes, arrange them in series or parallel or some combination of series and parallel, and wind up with the system lifetimes T1 through Tn. What's another operation? Another thing we can do is just take one of these random variables and multiply it by a constant k. So you can see there's a long list of operations on lifetimes. But here is a question that comes up. We want to know whether the distribution classifications are retained after an operation is performed on lifetime. This is often known as closure. In other words, if we start out with these n lifetimes and they have a particular characteristic, let's say they're in the IFR class, if we take this first operation, which is adding them up, is that also in the IFR class? So we'll be looking at that occasionally as we go forward. So here is a question. Is the IFR distribution closed under the formation of a coherent system? Which is to say, if each component has an IFR distribution, which is it's wearing out basically, does the system have the IFR distribution? In other words, if all of the components in a coherent system either have a constant failure rate or they degrade with time, that is, we have wearing out component, does that mean that the system also degrades? Well, this almost seems like an obvious question. If the components are getting worse with time, then the system seems like it would get worse with time. So the intuition here says, yes, of course that's the case. But in reality, when you do the mathematics, the answer is no. And the approach we're going to take here is we're going to try to find a counterexample that shows where the system is not wearing out when in fact the components are in the IFR class. And it turns out we've already encountered this counterexample, and it is this system right here. We've got two independent components. This first component is the weaker of the components, and the second is the stronger of the components, and they are placed in parallel. So this is a two-component parallel system, and we don't need to go through the math because we've already done it before. Here is the hazard function. You would assume that this would be monotonic, but it's not. It is non-monotonic. In fact, it starts down here at 0, increases for a while, and then when you hit a certain point, it decreases. So it is in the UBT class. So we form this very simple system of two components whose lifetime distributions are both in the IFR class, and yet when we place them into a system, what happens? That system has a hazard function that's in the UBT class. So the next two slides are going to be an explanation for why this particular phenomenon happens. Here's the explanation. The reason that the system lifetime is not also in the IFR class is explained in terms of mixture distributions. Now, for this two-component parallel system, there are only two interesting points in time, and the first point in time is when the first component fails. And by first component, I don't mean component 1, I mean the initial component failure time. So along a time axis, here is where that first failure time occurs. Then the second event is when the other component, which is still hanging on, fails, And that, of course, for a parallel system will result in system failure. And on the time axis down here, that happens right here. Well, to take these two event times of interest and make them a little more quantitative, we're going to let x1 be the minimum of the two lifetimes. Now, t1 is the lifetime of component 1, and t2 is the lifetime of component 2. So this x1 right here in the picture is the minimum of those two values. Now, what is x2, which is the time to the next component failure? Well, it's going to be the maximum of t1, and then we subtract, maximum of t1 and t2 minus the time of the initial component failure, which is x1. Through all of this, the system lifetime is going to be the sum of x1 plus x2, and that will give you the system lifetime t. So here are a couple of results. First of all, we know from the setup from the previous page that t1 is exponentially distributed with a failure rate of 1. We also know t2 is exponentially distributed with a mean of 2. Now remember that the expected value of t1 is going to be the reciprocal of the failure rate, so that's going to be a 1. But the expected value of t2 is going to be the reciprocal of 2, so that's going to be 1/2. And that's where we get component 1 being the stronger of the two components and component 2 being the weaker of the two. Next, x1, which is the minimum of t1 and t2, that's the way we defined it up here. Well, you know that the minimum of two independent exponential distributions is also the exponential distribution, but this time its failure rate will be the sum of the two failure rates of the two components, so that's 1 plus 2 equals 3. Now that's setting up the notation for the explanation. Here are the details. We know that x2 is independent of x1. How come? Because whichever one is the surviving component, that is exponentially distributed and therefore has the memoryless property. So x1 and x2 are independent. The next thing is x2 is a mixture, and that's the key here, of two random variables. It turns out that the probability that component 1, and component 1 is the stronger component, is the first to fail, has probability 1/3. We won't go into the details why that's true. We're going to hit a result later that shows why that's the case, but we'll for now take that as a given. It is not surprising that that number is less than 1/2 because component 1 is stronger than component 2. Now, the probability that component number 2, which is the weaker component, is the first to fail, is the probability T2 is less than T1, and that is 2/3. Not surprisingly, 1/3 plus 2/3 is equal to 1 because one of those two components is going to fail first. Now, the survivor function of x2 is a mixture. And with probability 2/3, which is the more likely case, x2 will be exponential 1. But with probability 1/3, and that corresponds to the first component failing, you will have a survivor function which is exponential 2. Now remember, this is a survivor function. You can then go to the hazard function by the 5x5 matrix, and that just says take the opposite of the derivative in the numerator and put the survivor function in the denominator, and you wind up with this quantity right here. Well, if you were to plot that out, you will see that that is in the DFR class. So back to the explanation. As time goes on, right, it increases for a while, and then it hits a point to where it starts decreasing. And the reason it starts decreasing is the longer time goes on, the more likely that this component is one of the stronger components, and that gives you a increasingly lower hazard function, and that's why you have it decreasing here after a particular time.